In this video, we are going to look at pyrometallurgy of iron. In this case, we are going to learn how we can extract iron from its iron ore by using pyrometallurgy. Now, the most important sources of iron ore are we have hematite and magnetite. Now, there are four ores body, but in this case, these two are very important and they are mostly used in what extraction of this iron from its iron ore, right? And also the reduction of the iron oxide, we need to reduce its iron oxide. The reduction of iron oxide to the metal, which is the iron metal, is accomplished by a furnace called blast furnace. Blast. I getting it? Yes. So this is how we do it. We get the iron ore and it's reduced by a furnace called blast furnace. And in the blast furnace, the reducing agent that we're going to use here is carbon monoxide. Now, when you look at your Elham diagram, you know that at temperatures at higher at 980 Kelvin, at 980 Kelvin, we know that can extract what we can use carbon monoxide as what reducing agent to what iron. Now let's look at the common iron bearing ore, right? Let's look at the common iron bearing ore. Now in this case, I told you that we focus on the two, which is magnetite and what hematite, but we have four. So let's look at the metal oxide, and their iron content is very important, right? So let's look at the magnetite. With magnetite, its chemical formula is Fe3O4, and it has iron content of 72.36%. Let's take note of that. And with hematite, we have Fe2O3, and its iron content is 69.94%. We have limonite and ilmenite, and they have their iron content to be 62.85 and 36.8% respectively. Now let's look at something important here. Quality of an ore depends on, in this case, the ore we are looking at is the iron ore. So the quality of an iron ore depends on, first, location. So they are saying that the quality depends on location. Why does it depend on location? So different regions, right? So you are taking the location, and I'm reading something about that. Different regions have varying geological conditions affecting the overall composition and the quality of the iron ore found in those areas. So due to the geological conditions, the quality of the iron ore might differ from different locations. So for you not to, because when extracting the iron from its iron ore, we look at the cost, right? So for you not to have much cost, you must look at where you are taking your the iron ore from. Now let's look at the second one, which is the iron content. The primary measure of iron ore quality is its iron content. The higher the iron content indicates a better quality ore, and as it provides more iron for the same weight, making extraction process more efficient, right? So we need the basic is that we need more iron content in the iron ore. I'm getting it. And let's move on to the water. Water content, the presence of water in iron ore can impact its handling and processing. Excess water may increase transportation costs. Transportation costs, because the ore will be very heavy, and also energy requirement during processing will be very high. So also increase that. So you must also check your water content of the ore I'm bringing in to cut down cost. The impurity content. So impurities such as silica, alumina, phosphorus, and sulfur can affect the quality of an iron ore. Lower levels of impurities are desirable as they impart efficiency of what iron, and it's very important. So that is very, very important. Let's take note of that. Let's move on to the next one, which is smelting of iron ore. In smelting, the ore is brought to what, a high enough temperature that the material melts. Are you getting it? And the final product is a molten metal. So the final product, we have two final product, a molten metal, that is a molten metal, and a slag. Right. The smelting is done so that the impurities are either carried off in a slag or are burned off as gas. That's what we do. We are trying to remove the impurities. That's why we melt. So let's look at this. What does this one mean? So for us to get change metal, the iron oxide to the iron metal, we need three things, which is we need a cook, we need the ore itself, and we need limestone. All these three play a significant role in a blast furnace, right? So the component of what, the charge in the blast furnace, it means that we add this to the blast furnace, we add this to the blast furnace, we add this to the blast furnace. Is we have the first one is what, iron ore. We have coke and limestone. Let's look at why do we need to add coke to it. We know the iron ore because that's the main source. We need to extract the iron from it. Now let's look at why we add coke. So the reason why we add coke is for three reasons, right? And the first reason is that the coke contains carbon, right? And it supply chemical reactant for reducing iron ore to metallic iron. As I said, that the coke also contains carbon, right? And so that in that case we could generate carbon monoxide from the coke, and then it serves as what, a reducing agent to reduce the iron ore to what, the metallic what, iron. The second one also is what, it acts as a source of carbon in the pig iron. Yes, because coke contains carbon. And for, let's look at something here. At the end of the blast furnace, what comes out is a pig iron. And in the pig iron, right? And in the pig iron, the percentage of carbon is 4%, right? It's 4%. So the coke also help what, as what, a source of what, carbon in the pig iron, and eventually in the steel too, right? Yes. And also the last one that we need to learn is that it's a source of heat in the blast furnace. It's also serve as what, fuel. So we have three things: reducing agents, serve as, we get carbon from it, and also serve as what, fuel. Let's go to the limestone. The limestone also serve as what, fluxes. We call it fluxes. Now when metal is smelted, the metal is separated from its impurities by melting, with the impurities forming a molten slag on top of the what, the metal. So we have, let me draw this like this. It's two like this. This is a molten, and we have like this. The top here is a slag, right? This side is a slag, and this is the what, the molten metal. Many of the impurities associated with the ore are difficult to what, to melt, and so they will what, not form a proper slag, and then they will know what, which retards the what, smelting process. So yeah, the impurities are difficult to what, to melt, so they will not form a slag. So for the impurities to melt, we add fluxes, right? And these fluxes, we have two fluxes, which is the dolomite and the limestone, right? And in this smelting of iron from using the blast furnace, we use the limestone, and the limestone chemical formula is calcium carbonate. Are you getting it? Calcium carbonate. Now, before the coke is added to the blast furnace, it's heated. So it's heated from what, a cooking oven, and the ore too is shaped into pellet and center. And also the limestone also is what, shaped into center. Let's look at what does the shape means, right? So let's look at the physical forms of what, iron charge. So when you look at center, center is just like this, and pellet is like this, and you see that pellet is more fine than center, and nodules, and so this is how they were meaning it. Have this before it is added to it. Yeah. Now let's look at some operations of some understanding of the blast furnace. So the blast furnace, let's look at some ideas of the blast furnace, because we've talked about the three things entering the blast furnace, which is the cook, flux, and the iron ore. Now, when we talk about the blast furnace, right, the function of the blast furnace is to produce pig iron, as I said. So the function, this is a schematic diagram of the blast furnace. The function of the blast furnace, right? So the blast furnace. So the function of the blast furnace is to produce what? Pig iron. So it's to produce pig iron. And as I said, pig iron has 4% weight of what? Carbon. I getting it? Yes. And not steel. So the blast furnace produces pig iron, right? But not steel. I getting it? Yes. And a blast furnace is a shaft furnace, right? In which a blast is preheated, air is blown through the turrets at the bottom. So this gas is heated and is blown through the turrets, right? And then it goes inside and it starts the reaction. Am I getting it? Yes. Now let's look at something here. We're going to look at the flow sheet of steel. Actually, for us to produce steel, which steel contains what? Combination of carbon and iron. In this case, the carbon content is about 0.018%. Carbon is very low, and we add some alloying elements. So let's look at the flow chart for the process of steel, but we are looking at pig iron in this case because we end at the blast furnace. So we have the cook, which serve as three purpose reducing agents, serve as cook and also fuel, that's carbon. We have the ore, and we have the what? The limestone is added, and this is preheated. Preheated, change it to the blast furnace. The blast furnace will heat and reaction will take place, and we'll get what we get here is pig iron. We are going to get pig iron here, pig iron, right? Because at the end of the blast furnace, the product that we get is pig iron. Now, for steel making, we add some alloying elements, which is manganese, chromium, titanium, and niobium, right? So all these are added as what? Alloying element. And at the end of the ladder, we had here will be what? Steel. And steel contains less amount of what? Carbon. Are you getting it? Yes. In this case, we've done that way. So this is the flow sheet for our for this video. Our most important thing is to end at the pig iron here. So cook or limestone, which is a flux, added to it, the blast furnace, and reaction will take place. At the end we get two molten, that's a molten metal and a slag, and then get pig iron as a molten metal when it has high amount of carbon. Now let's look at the blast furnace operation, but before then let's look at some parts of the blast furnace. So the blast furnace, the components of the blast furnace, right, is in three parts. We have the stack. This is the stack, as you can see from this side to here is a stack. We have the Bosch. This is the Bosch where reaction take place. A hat. We have the hat. So we have the stack, the Bosch, and the hat. I getting in all this. They have the function that they play. So let's look at something in the blast furnace. So we are talking about the stack. So for the stack, in the blast furnace stack, there is what? A counter current flow of gases and solid. In the stack, hematite or magnetite is reduced to what? Sponge iron by the action of what? Carbon monoxide. So in the stack here, that is where you see the gas is introduced into the turret and it comes, and then the also is placed inside and it's coming counter currently, right? So a reducing agent, what is called carbon monoxide, is formed, and then this reducing agent reduce the carbon and reduce the iron ore, which in this case can be hematite or magnetite. So reduction happens at the stack. I get it. So reduction happens at the stack. Let's look at the Bosch. What happens? This is the part of the furnace where the content melt. So melting takes place at the what? The Bosch. Melting takes place at the Bosch, right? And also several chemical reactions take place at the Bosch, and this is where the slag is formed. So we get slag, melting takes place at the Bosch, slag is formed at the Bosch, and then we move on to the what? The hat. So when we talk about the heart, right? In the heart, this is the heart. In the heart, in the heart, molten pig iron and molten slag is segregated from each other and are trapped up separately. So this is where separation happens, right? We get molten, after the melting, we have two products, the molten metal and the slag. So it's segregated, both the molten metal and the slag is segregated. This is separated, and then we get the metal, which is the pig iron, and then the slag, right? Now we want to look at the operation of blast furnace. This is the operation. That what I was saying is the type, the part of the blast furnace. Now the operation of the blast furnace, right? The blast furnace, right? The blast furnace is charged with what? Iron ore, limestone, and what? Coke. I getting it? And we add the limestone serve as flux, and the coke serve as fuel, and also it help in what? Providing reducing agent for it. And the ore is shaped in what? Lamps, which is a pallet or center, right? Are you getting it? These are carried to the top of the furnace. So you can see that it's here. They are carried to the top of the furnace. Carried to the top of the furnace. With what? A skip or what? A conveyor. So we don't just, this blast furnace is very big. It's very huge. You don't just put it there, but with a transportation system, which can be conveyor system, right? Now, meanwhile, you can see meanwhile, where is the air? Meanwhile, right? Meanwhile, air preheated to 900 degrees. So air preheated to 900 degrees is injected through the turret. So it's injected through the turret. This is a turret, right? Through the turret, which are nozzle, right, at the bottom of the furnace. So which are nozzle at the bottom of the furnace. So we have the nozzle at the bottom of the furnace, and it's the air coming in is heated, preheated as what? 900 degrees, right? 900 degrees at very high degrees. The coke is partially bent. Look at this. The coke is partially bent by the injection of what? Air, both to produce heat and to generate carbon monoxide. So when the hot air is injected, counter current the flow of the what? The coke coming in, and then it what? Converts the coke into what? Carbon monoxide. I getting it? So it's generates the coke to carbon monoxide, and also the coke is also serve as fuel, which generates also heat. Are you getting it? Yeah. Now, since the coke is relatively expensive, some furnace inject coal or oil along with the air as a supplementary fuel, reduce the coke. The carbon monoxide travels upward, right? So the carbon monoxide travels upward through the column and remove oxygen from the iron ore on the way down, leaving metallic iron. So we introduce hot air, and this hot air countercurrent the flow of what? The coke coming in. It reduces the coke to carbon monoxide, and the carbon monoxide serves as what? A reducing agent to the what? The ore coming in, and then it reduces the what? The metallic oxide to metallic iron. Are you getting it? By the time the charge reaches the base of the furnace, the heat generated there melt the iron. The resulting molten or the hot metal is tapped the regular interval by opening the what? The tap hole in the bottom of the furnace so that it can flow out. The flux is combined with the impurities and the coke and the ore to form what? The slag, which floats on what? Which floats on the surface of it. I getting it? The hot metal from the furnace is collected in a special constructed railway containers called the what? Torpedo cars. A torpedo carries the molten iron. They're still making furnace. Carries the molten iron to this. And the blast furnace are operated continuously without shutdown 10 years or more. So let me, the operation of the blast furnace is that the ore, limestone, and coke is added at the bottom of on the top of the blast furnace. So and then we inject hot air, which is what heated at what? 900 degrees. We injected it here through the turret. So as it goes, it also reacts with the coke. The coke reacts with it reacts with the coke, then brings the coke down to reducing agent, which is carbon monoxide. The carbon monoxide also what reduces the ore coming in, which in this case can be hematite or magnetite, to what, from metallic oxide to what, metallic ion metal. And then when the metallic ion is coming down, you have heat generated at the base of the blast furnace. Due to the heat, it melts the metallic ion. Fluxes are also added, right, what react to the impurity so that they will float on what the surface of the molten metal, and then it's segregated differently. I get it. In the molten metal, which in this case the pick ion is sent forward to making process. Let's look at various temperatures and what happened. Right. So I told you that the melting temperature of iron is 1529. So let's look at this. Feed is charged on top of the blast furnace. So this is the stock line. At 400 degrees, what happened is that the iron oxide react with what? Carbon monoxide form the so we have hematite reacting with what? Carbon monoxide form magnetite and carbon dioxide. And we have hematite reacting with carbon monoxide to form carbon dioxide and what? Iron and carbon. So this is reduction. That's reduce it to what? Iron. But now we have magnetite reacting with carbon monoxide to form what? Iron oxide and carbon dioxide. Now at 850 degrees, we know that the iron oxide reacts with the reducing agents, which is the carbon monoxide, to produce the metallic ion carbon dioxide. And also when it produces that, the limestone here, which in this case calcium carbonate, breaks down. So the limestone breaks down to form calcium oxide and what? Carbon monoxide. That is at 850 degrees. And these are the heat enthalpy, right? Now let's move on to so from here, from 400 to 1000 degrees, have the metal still being in what? A solid form. Are you getting it? Now, then when you go above 1000 degrees, we know that carbon, because that place is where air is what? Injected to the trace and react with the coal coming in. So see, the carbon reacts with what? Carbon dioxide to produce what? Carbon monoxide. In this case, this is what? The reducing what? The reducing agent, right? The reducing agent, which helps in reducing the what? The iron oxide to iron metal. Now we have the silicon oxide, that's the silicate, reacts with what? The coke to produce, break down to form silica and what? Carbon monoxide. In that case, we have another what? Reducing agent here. We have iron sulfide. If they are sulfur inside, reacts with what? The limestone, which has break down to calcium oxide plus carbon, form what? Calcium sulfide and what? Iron and what? Carbon monoxide. Have all these are what? They are slag. So magnesium oxide, phosphorus oxide, the silicate, right? So wherever you see the oxide for the slag generated, we have aluminum oxide, the slag. We have SiO2 is a slag. We have MnO is a slag. We have P2O5 slag. All these lists, you being able to identify the slag will help you to know how to calculate for the material balance. So in my next video, I'm going to talk about the material balance of iron, and in this case with some calculations, right? Thank you very much for watching this video. I hope